Waves introduction. In this lesson, we're covering what are waves, the types of waves, transverse versus longitudinal waves, frequency, hertz and period, amplitude, crests, troughs, and wavelengths, and then the universal wave equation. Waves. Waves are disturbances which transfer energy over a distance. They all originate from vibrations, for instance, dropping a pebble into water. The vibrating source supplies energy which is transported along the medium as a wave. This vibration can be caused by many things, from moving a string, rubbing objects together, or having an object impact the ground or water. So for instance, seismic waves are waves of energy created by earthquakes which travel through the earth and are caused by tectonic plates moving against each other. Waves pass their energy from one particle to another until it runs out of energy. So for example, water waves created from tectonic activity, volcanic eruptions, winds, impacts, etc. carry a lot of energy which can be used to inflict serious damage. Now we're going to be discussing two main types of waves, transverse waves and longitudinal waves. Transverse waves have a very distinct pattern. It's this oscillation of up, down, all the way across. In this case, the particles vibrate perpendicular to the direction of motion. So we're going to be vibrating up and down, and yet the direction of motion in this case is to the right. So the vibration is perpendicular to the direction of motion. That's how we're going to know that it's a transverse wave. The other kind of wave is called a longitudinal wave. In this case, the source vibrates parallel to the direction of motion. So an example of this would be sound waves. So what happens in sound waves is that you get a burst of energy coming out of something like a speaker or someone's mouth, and that compacts the air particles in front of it. As it does, it creates what are called compressions. When those compressions ease up, we get what's called an expansion. So a longitudinal wave is a combination of compressions and expansions as the wave propagates from point A all the way down to point B. Terminology. Regarding any kind of vibrating object, one complete oscillation is called a cycle. The number of cycles per second is called the frequency, and the unit for frequency is the hertz. The time required for one full cycle is called the period, and the unit is generally seconds, but it can be days, months, years, etc. So in this case, in the bottom, this would be one complete cycle. You're going to start at the bottom, you're going to go to the left, you're going to go back to the bottom, you're going to go to the right, and you're going to end at the bottom again. Frequency and period are inverses of each other. So F is going to equal to 1 over T, and T is going to equal to 1 over F. So if you had a frequency of 0.5 hertz, then the period would equal to 2 seconds. Amplitude is the distance from rest position to maximum displacement. So when we're taking a look at a transverse wave, that's when we go from the baseline here all the way up to a peak. This would also be an amplitude here. And when we're talking about a pendulum, the amplitude of a pendulum would be this distance here, the maximum displacement from center to center. Check your understanding. A mass hung from a spring vibrates 15 times in 12 seconds. Calculate the frequency and the period of the vibration. So frequency is going to equal to cycles per second. We're told that it vibrates 15 times in 12 seconds, giving us a frequency of 1.25 hertz. Now we need 2 sig digs, so our final answer becomes 1.3 hertz. B asks for period. Period is equal to 1 over F. Now we need to use the 1.25. So 1 divided by 1.25 equals to 0.8 seconds. That means it takes 0.8 seconds to complete one oscillation. Now what do these two numbers mean? Well, it means that you can do 1.25 oscillations per second, and it takes each oscillation 0.8 seconds to complete. Check your understanding. The amplitude of a child swinging on a swing is 1.2 meters. What total distance does she travel after 3 complete cycles? Okay, so let's draw this out. So if that's the base position, and that is maximum displacement, and we're told that her amplitude is 1.2 meters, and we're asked for what total distance does she cover in 3 complete cycles, well, we need to count how many times she does this 1.2 meters. So we're going to go from here to here, 1, and then back 2. Then we're going to go back out to here, that'll be 3, and then it's got to come back to rest position, 4. The distance for one oscillation is going to be 1.2 times 4, and there are 3 oscillations, so we get 1.2 times 4 times 3, and that equals to 14.4 meters. Now we need 2 sig digs in our answer. This 3 doesn't include because it's an infinite number. It's 3 cycles. The only number we're using in our actual calculations is 1.2. So your final answer becomes 14 meters. Now a few more terms. Crests on our transverse wave you're going to be able to see very easily are the ones at the top. The troughs are the ones at the bottom. So the lowest point, that's going to be your trough, and the top point, that's going to be your crest. The wavelength is the distance from crest to crest or trough to trough. Universal wave equation. So we recall our formula V equals D over T. We can use that here. So regarding waves, the distance traveled is the wavelength. So that's lambda right there. And the time is the period, so T, which is the time to complete a wavelength in seconds. Therefore, V equals lambda over T. We're substituting D for lambda and little t for big T. And since F is equal to 1 over T, we get our universal wave equation, V equals F lambda. The wave equation works for all waves, visible and invisible. So that means things like water waves and electromagnetic waves, like microwaves, gamma rays, etc. Check your understanding. The wavelength of a water wave in a ripple tank is 0.080 meters. If the frequency of the wave is 2.5 hertz, what is its speed? So let's write down what we have. We have lambda is equal to 0.080 meters. We have frequency 2.5 hertz, and we're looking for speed. We know our equation, V equals F lambda. We're going to substitute our numbers in. 2.5 times 0.08 equals to 0.2 meters per second. Now we need 2 sig digs, so our final answer becomes 0.20 meters per second. And there's no direction. Check your understanding. The distance between successive crests in a series of water waves is 4 meters, and the crests travel 9 meters in 4.5 seconds. What is the frequency of the waves? Okay, so what do we have? Well, we have the distance between successive crests, otherwise known as lambda, is 4 meters. We're told that crest to crest or trough to trough is 1 wavelength, so the distance between successive crests in a series of water waves would be the lambda of 4 meters. Now V, we're not told outright, but we know it travels 9 meters in 4.5 seconds. Therefore, V is going to equal to 2 meters per second, and we're looking for frequency. V equals F lambda. F is going to equal to V divided by lambda. 2 divided by 4 is going to equal to 0.5 hertz. Now we need 2 sig digs in our answer, so our final answer becomes 0.50 hertz. Check your understanding. The period of a sound wave from a piano is 1.18 times 10 to the negative 3 seconds. If the speed of the wave in the air is 3.4 times 10 to the 2 meters per second, what is the wavelength? So we're told period is 1.18 times 10 to the minus 3 seconds. V, we're told, is 3.4 times 10 to the 2 meters per second, and we're looking for lambda. We know V equals F lambda, and since F is going to equal to 1 over T, we can rewrite it as V equals lambda over T. Lambda is going to equal to V times T. Lambda is going to equal to 3.4 times 10 to the 2 times 1.18 times 10 to the negative 3. That equals to 0.40 meters. 2 sig digs, and that is what we need. And that concludes our Introduction to Waves lesson.